Howdy, today on Flipping Science looking at cleaning agents. So you need to be able to talk about using nonpolar solvents to dissolve nonpolar materials, polar solvents to dissolve polar materials, describe and explain how soaps and synthetic sulfonate detergents remove grease, write equations for alkaline hydrolysis of triglycerides, and write an equation for the formation of magnesium or calcium precipitates from soap, given the structural formula of the soap anion. So why do we bother about removing stains? Well, it's not economical or sustainable to replace your clothes every single time you get them a little bit dirty. You wouldn't burn your clothes after you've worn them a few times because they start to smell, instead we clean them. So by cleaning and removing stains, we can reuse the clothes over and over again. So getting rid of stains is all about secondary bonds. So what we have is a stain and a solvent to get rid of the stain, and we want to match the bonding type between those two. So the way it works is we've got a solvent down here, for example, and our solute here is our stain. You agitate them together and you get the solute interacting with the solvent in a way that they both dissolve in each other. And that way you can get rid of the solvent with the stain inside it, the solute, and wash that away from your clothes. So that's how you get rid of the stain. So the ease with which this happens depends on the nature of the strength of the secondary bonding between the solvent and the solvent, the solute and the solute, and the solvent and the solute. So if you have really strong bonds between the solvent and the solute, you get very good solubility, and that's what you want to have in order to get your stain out of the clothes. If you have strong bonds between the solute particles, it'll be very difficult for them to be dissolved in the solvent. And if you have strong bonds between the solvent particles, it'll be difficult for the solute, so the stain, to dissolve into the solvent. So you need to match up your polarities very carefully. So let's start by looking at water. So water shows extensive hydrogen bonding between the water molecules. And it's a very polar molecule. So in terms of the stains that we can get rid of with water, things that will interact with water very strongly will be easily gotten rid of. So if we look at the fact that water is polar, so it's got a negative end and a positive end. So if we had something like a salt stain, the salt can be dissolved by the water fairly readily usually. The negative end of the water molecule is attracted to positive ions in the salt stain. The positive end of the water molecule is attracted to negative ions in the salt. And they interact and they get pulled apart, so we get ion dipole bonding occurring. Water is also good for polar stains, so similar idea. So if you've got a polar molecule, that is your stain, the water is polar as well, so the water interacts with the polar stain and dissolves it, and then you wash away the water and you get rid of your stain. If you've got non-polar stains, you need to use a non-polar solvent in order to get rid of it. When we're talking about non-polar stains, we're talking about greases, so grease, fat, oil, that kind of thing. So you might have had this dribble on your shirt before. You try and wash it out with water, and water doesn't work very well. So in order to get it out, you need to use a non-polar solvent. The way this works is you get dissolving of the non-polar stain from the non-polar solvent because they're attracted by dispersion forces. So there's dispersion forces acting between the non-polar solvent and the stain, and they're comparable in strength between the dispersion forces of the fat with the fat, or the oil with the oil molecules, and that way you can get them dissolving and coming out. So down here we've got tetrachloroethene. That would be very handy for getting rid of non-polar stains, for example. When you talk about dry cleaning, dry doesn't mean dry as in the clothes don't get wet, it's just you don't use water. So you use a non-polar solvent to do the dry cleaning. So soaps and detergents are called surfactants. They're surface active cleaning agents, and they're used to remove grease and oil. They both have long carbon chains. So here's a soap over here with a really long carbon chain. And here's a sulfonate over here, so this is a detergent with a long carbon chain as well. So we've got a long carbon chain, but what differs is what you get at the end. So in a soap you have a carboxylate head. So here we can see a C double bond O minus group, so that's a carboxylate salt, a carboxylate anion, and we've got sodium there, so that would be a sodium carboxylate salt. Detergents have a sulfonate head, so they've got a sulfur and some oxygens around them. Another difference is normally with a detergent you'll have a benzene ring involved in the structure, so you might have a double carbon-carbon double bond in here as well. That'll give that a different structure. So rather than being straight, like the soap is, the detergent often has some kinks in it. So how do soaps and detergents remove stains? Grease is made up of fats and oils, and that makes it very non-polar. So if we have a look at our picture down here, there's long carbon chains. and they're non-polar. So this black bit down here, that's our stain, and it's on our shirt, for example. The soaps and detergents are made up of a non-polar tail and a polar head. So if it's a soap, like I said, it's a carboxylate salt. If it's a detergent, it's a sulfonate. What happens is the non-polar tail of the soap or detergent dissolves in the non-polar grease. So we have a matching polarity there, so they dissolve together. The ionic head, however, that's got a charge, so that's not going to be attracted to the non-polar grease. The ionic head, that's going to be attracted to the water molecules that you're probably using to get rid of these stains. So surrounding here we have a lot of water. With ion-dipole bonding, you're going to get attraction between the water molecules and the negative ends of the soap or detergent. What also you get is repulsion between each negative end of the detergent or soap molecule, because they don't like having two negative heads close together. So they repel each other as well. And what that does is, if you agitate it, is you get the grease being lifted off of the surface and it gets surrounded by the soap or detergent molecules. So again, the non-polar tail of the soap is attracted to the grease, the polar head of the soap is attracted, or detergent is attracted to the water, and you get this structure forming here called a micelle. So you agitate the grease with your soap or detergent, the non-polar end of the detergent dissolves into the grease, the polar end of the detergent is attracted to the water, so it stays pointing towards the water. You get mutual repulsion between the negative ends, and you get a micelle forming, which then removes itself from the surface, then you just wash it away. This is why when you do your dishes, the colour of the water starts to go brown after a while. That's all these micelles that are floating around in the water. So, how do you make a soap? Soaps are made from the alkaline hydrolysis of fats and oils, and it's a process called saponification. You take your fat or oil, you react it with sodium hydroxide, you heat it up, and you get alkaline hydrolysis happening. So with alkaline hydrolysis, what happens is the fatty acids from the fat break off, and you get carboxylate salts forming, and what's left over is glycerol. The glycerol is kind of filtered out and used for other processes. What's kept for the soap is the carboxylate anions down here. In this case, because we use sodium hydroxide, we're getting a sodium carboxylate salt. And that's going to be our soap that's used. It's like any alkaline hydrolysis of an ester, you get a carboxylate salt being produced and glycerol. And that's all that's happening here. So let's have a look at a question. The only cleaning agents recommended for use on ancient coins are soapy water or CF3CCl3, which is a non-polar solvent. Describe and explain how both soapy water and CF3CCl3 remove grease from coins. So first I'll just draw the structure of CF3CCl3 so we can see what we're working with. So carbon, and fluorine, Cl. Okay, so there's our structure. If we have a look at this, we can see it's very non-polar. Even though the bonds between the carbon and fluorine and carbon and chlorine are quite polar, the way they're distributed in 3 dimensions around the carbons mean that the center of negative charge is going to be right in the middle of the molecule, which is the same location as the center of positive charge. So they're going to balance each other out. So we have a non-polar solvent. So let's start talking about that. So if you've got grease on your coin, you want to get rid of that with a non-polar solvent if you can. So the grease is going to be non-polar, so you need to use something that's non-polar to dissolve the grease in it. So you're going to get dispersion forces active between the CF3CCl3 and the grease, and you can use that to remove the grease from the coins. The other thing is we've got soap in there as well, so how does soap remove grease from the coins? So the grease, again, it's non-polar. The non-polar tail of the soap molecule dissolves in the grease. The ionic head stays attracted to the water molecules that are surrounding it. So you get ion dipole attraction between the water molecules and the ionic head of the soap. You get repulsion between each ionic head of the soap, and that acts to pull the grease off of the surface, and you get a micelle forming, and then you wash that away. So today at Flipping Science, we looked at how to get rid of stains, how soaps and detergents are structured, and how soaps and detergents get rid of greasy stains. So that's it for Flipping Science today. See ya.